In this video, we'll continue our discussion of causal graphs by exploring their capacity to serve as statistical models. Recall that causal graphs are directed acyclic graphs, DAGs, that represent causal relationships between variables. An example adapted from a 2008 study of judicial decision-making is shown here. Other than judicial decision, the nodes represent characteristics of the judge in blue, or characteristics of the case that the judge is assessing in orange. Some variables, like judge demographics and case characteristics, actually represent an aggregation of several variables, and for simplicity, we'll treat them as a single variable in this video. A directed edge between two variables indicates that the parent variable is a cause of the child, with the direction of the arrow indicating the flow of time from cause to effect. The graph being acyclic is a reflection of time not flowing backwards. When we say that x is a cause of y, this means that the value of y depends on the value of x. In other words, y is a function of x. So while it may seem odd to have an arrow from case characteristics to judge demographics, because how can anything cause demographics like age and race? What that arrow means is that the values of the judge demographic variables in this context do depend on case characteristics. This can happen if certain types of legal cases, perhaps depending on the subject matter, tend to be brought before certain types of judges. This graph serves as a statistical model for our data because it helps us understand how the different variables would be expected to be related. For example, since judge ideology is caused by judge demographics in this model, we would expect to see correlation between demographics and ideology. And since judge ideology is the cause of the judge's decision, we would expect to see correlation between the decision and ideology. And we would also expect correlation between the decision and demographics because of this chain of causes. In particular, we can view all variables in a causal diagram as random variables. And the fact that variables are functions of their parent nodes means that the probability distributions of each variable can be expressed as being conditional on its parents. So let's look at how we might write down this joint distribution. One way to do this ignores the structure of the graph. We can ignore the causal relationships between variables and express the joint distribution purely by using the definition of conditional probability. Pause the video here and verify that this product is a way to express the joint distribution. When we take into account the graph structure and make a certain independence assumption, it turns out that we can express the joint distribution of all 5 variables a little bit more succinctly. Let's take a look. The joint distribution will end up looking similar to what we just had, but we'll approach expressing this distribution in a generative way. In other words, starting with the variables occurring earliest in time and using those variables to generate ones occurring later in time, their descendants. Because case characteristics is parentless in this model, we can start from there and include P of CC in the product, representing the marginal probability of this variable. A parentless variable in a causal DAG is also called an exogenous variable because it's external to the system that we're studying. It's not to say that the case characteristics variable truly has no causes. It just means that its causes are not relevant in our particular situation. Because if we had to always care about all causes of all variables, we'd actually have to trace causes back to the beginning of time, which is both impossible and unnecessary. The remaining variables that have parents are called endogenous variables and have their values determined by exogenous variables and other endogenous variables. The judge demographics variable is a function of just case characteristics, so we can add the conditional probability P of dem given CC to the product. Ideology is a function of both judge demographics and case characteristics, so we can add the conditional probability P of I given dem and CC to the product. So far, our joint distribution expression is looking identical to the one that ignored graph structure. Employment history is a function of judge demographics, so we can add probability of EH given dem. This is where our representation departs from and becomes more compact than the structure agnostic expression. In causal graphs, we assume that conditional on the values of its parents, a variable is independent of all variables in the graph that are not its descendants, its non-descendants. This is known as the causal Markov assumption or the causal Markov condition. For example, employment history is independent of both ideology and case characteristics, its non-descendants, given judge demographics, its parent. Recall that the definition of conditional independence allows us to break a joint probability into a product and can also be rewritten to show the relation at the bottom. The conditional distribution of employment history, given ideology, case characteristics, and judge demographics, really only needs to depend on demographics. Judge ideology and case characteristics provide no further information about employment history once we know about judge demographics. Returning to our decomposition of the joint distribution, the fact that the employment history term is only conditional on judge demographics is a result of the causal Markov assumption. Finally, judicial decision is a function of all four other variables, so we can add P of JD given I, Dem, EH, and CC. The product of marginal and conditional probabilities here is a way to decompose the joint distribution of all variables and is known as the product decomposition rule for DAGs. To put the product decomposition rule in full generality, we can say that the joint distribution of a set of variables in a causal DAG is the product of the conditional probabilities of each variable given its parents. And for exogenous variables, which are parentless, this conditional probability is just a marginal probability. What we've done up to this point is to clarify the general probability structure of the joint distribution, but to complete the process of specifying the joint distribution, we would need to specify the forms of these probabilities. For example, what is the probability mass function of the case characteristics random variable? And how exactly does employment history depend on demographics? Maybe employment history, if it's measured as years of experience, is normally distributed, and the mean could be given by a linear regression model. For example, if demographics had 3 categories, the conditional mean of employment history could be expressed with this linear regression model. This would give 3 means for years of employment for those 3 demographic categories. Beta 0 as the first mean, beta 0 plus beta 1 for the second mean, and beta 0 plus beta 2 as the third mean. In the same spirit, we could specify functions for how judge demographics depends on case characteristics, how judge ideology depends on demographics and case characteristics, and how judicial decision depends on all 4 other variables. The specification of the explicit functions governing how each variable depends on its parents is the specification of what is called a structural equation model. The causal graph alone does not provide a full specification of the joint distribution of the variables in the graph, but combined with a structural equation model, the full distribution can be clearly specified. In summary, causal graphs are statistical models because they encode relationships between the random variables representing our study variables. In this video, we've laid out the framework for how graphs tell us about probability distributions of variables. Next, we'll explore some key structures, arrow configurations, within causal DAGs. These structures represent fundamental causal relationship patterns that give rise to associations in data. These structures will give us direct insights into how lack of exchangeability arises so that we can understand how to achieve conditional exchangeability to estimate causal effects.